Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today's topic is rotation, review number 5. So ring of mass m, radius r, and a rotational inertia mr squared is initially sliding on a frictionless surface at constant velocity v0 to the right. At time t equals to 0, it encounters surface with the coefficient of friction mu, and it begins sliding and rotating. After traveling distance L, the ring begins rolling without sliding. Express all answers to the following in terms of mr, v0, mu, and the fundamental constants as appropriate. A. Starting from Newton's second law in either translational or rotational form, as appropriate, derive a differential equation that can be used to solve for the magnitude of following as the ring is sliding and rotating. One is the linear velocity v of the ring as a function of time t. So they are asking you to derive a differential equation. We know differential equation is d something over dt usually. So starting from Newton's second law, we have to use translational form because you are asked to derive a linear velocity. So here first is differential equation. Make sure you underline that so you know what you are asked to do. The second one is linear velocity. For linear velocity, we have to use translational form, which is F net equals ma. What is the F net? As the ring rolling without slipping. The net force is the friction force. We know friction force is mu times Fn. Since the ring is moving in the horizontal direction, Fn is mg. So it's mu times mg equals negative ma. Why is it negative? Because friction reduce velocity, reduce speed. So this is negative. Acceleration is negative. In a sense, friction slows it down. We know m cancels, and it's a differential equation. We know a equals to dv over dt. Substitute everything in. You should have mu g equals negative dv over dt. This is the differential equation. This is the equation we have to use to find velocity. Next one, the angular velocity omega. So again, starting from Newton's law, we have to use rotational form because we have to find angular rotational velocity. So net torque equals I alpha. What is net torque? What force is producing the torque? Is friction force. So friction force is the one that's producing torque. We know torque is Fr. So you have mu mg times r equals I, which is mr squared times alpha. There is no negative sign because this friction actually speeding up the rotation, make it rotating faster. So there is no negative. Again, m and m cancels, and alpha equals to d omega over dt. This is the differential equation part. Plug everything in, you'll have mu g over r should be equals to d omega over dt. This is the differential equation for the angular velocity. Next part, derive the expression for the magnitude of the following as the ring is sliding and rotating. First, you have to find linear velocity. From the differential equation, in last part, we have mu g equals negative dv over dt. So we have to integrate to find v. You switch it up, multiply dt on both sides. You have mu g dt equals negative dv. Then you integrate. T is from 0 to t. V, you started with v0. You ended up with v. So mu g is constant. You can factoring it out. On the left side, you'll have mu g t minus 0. On the right side, you're factoring negative out. It just becomes v minus v0. Rearrange this equation, you can find v equals v0 minus mu gt. This is a v as a function of t. The angular velocity omega as a function of time, you do the same thing. From last part, you have differential equation for omega. So move it around. D omega equals mu g r dt. Again, t is from 0 to t and omega is from 0 to omega because you were sliding before. Now, so your angular velocity is 0. You've ended up with omega. So you'll have mu g r factoring it out. t minus 0 on the right side is omega minus 0. So omega equals to mu g divided by r times t. Next part. Derive an expression for the time it takes the ring to travel the distance L. Let's see what we know. You need to find the time. So for the ring to travel at a distance L, what happens? It's rolling without slipping. So we know at a distance L, the ring is rolling without slipping. This is a special condition. What does this tell us? Is V equals to R times omega. At this time, we know what V is. From part B, we know what omega is. So we set up V equals R times omega. V equals R times omega. So R cancels out, rearrange it. You'll have V naught equals mu gt plus mu g times t. So you have t equals V naught divided by 2 times mu g. That is the time. Next part, derive an expression for the magnitude of velocity of the ring immediately after it has traveled the distance L. So what do we know? We know that at distance L, the ring is rolling without slipping. We already figured out the time. We also know initial velocity is V naught. We also know acceleration, linear acceleration, is negative mu times g. You have to find final velocity. Final velocity is V naught plus at. And that equals V naught minus a equals mu g, negative mu g, and t is V naught over 2 mu g. So you simplify this, you'll have V naught divided by 2. Last part, derive the expression for the distance L. So again, this is kinematic question. What do we know? We know at distance L, again, the ring is rolling without slipping. We know the time. We know the initial velocity. We also know the velocity at L is V naught over 2. You have to find the distance. There are many ways to find the distance. I will use this equation. The distance is average velocity times time. I can find average velocity because acceleration is constant. Average velocity is just V naught plus V over 2, and here's the time. Plug that in, you should have L equals to 3 V naught squared divided by 8 mu g. That's it. I hope that helps. See you next time. Thanks for watching.